All right, the next thing we're going to look at is what differentiability implies about continuity. So if f of x is differentiable at a point a, right? So we're back to at a point, all right, in its domain, then we know that this limit exists, right? That f prime of a is equal to this limit of f of x minus a over x minus a, right? That's just a definition of the derivative at a. And if it's differentiable, then that limit exists. So let's notice that if we look at just the numerator of that limit, f of x minus f of a, that is the same thing as f of x minus f of a over x minus a times x minus a, right? I mean, all we did was divide by x minus a and then multiply by x minus a, and so we basically multiply by 1, right? So it doesn't change the value. So that's I think I can convince you that that is a true statement. Now let's look at taking the limit of both sides. All right, we're going to take the limit of both sides of these of that previous equation, and so if we on the left hand side, we can distribute that limit, right? Because we know that f of a is just a constant, right? It's f of a is just whatever the value of the function is at a, and we've said that a is in its domain, so it has to exist. And so we can sort of distribute that limit using the properties of limits, right? And then on the other side, also, we said that this limit of the ratio of f of x minus a over x minus a has to exist, right? And because of the derivative, we said it's differentiable at a, and so that limit has to exist. So I can again distribute this limit on the right-hand side, okay? And now on the right-hand side, the first limit is just f prime of a, and as x approaches a, the limit as x approaches a of x minus a is 0. All right, so the whole right-hand side of this equation becomes 0, and so we know that the limit as x approaches a of f of x minus f of a has to be 0. Okay, and so if that's true, we could just add f of a to both sides, which tells us that the limit as x approaches a of f of x has to be f of a. Now, that goes back to continuity. That was our definition of continuity, right? The limit as x approaches a of f of x has to be f of a. Okay, and so, right, so we've started with the assumption that the function is differentiable at a point in its domain, and our conclusion is that if it's differentiable at a point in its domain, then it has to be continuous at that point. Okay, and that is the next concept that we want to look at is if f is differentiable at a, then f has to be continuous at a. All right. If that's true, then the contrapositive also has to be true, which means that if f is not continuous at a, then f is not differentiable at a. Okay, so we're going to look a little bit more at this in class, but that last statement made me think, well, what the heck? What about a function like this? All right, because when I look at this function, I'm thinking, well, I mean, the slope appears to be 1 to the left of 0 and appears to be 1 to the right of 0. And you can get as close to 0 as you want, and it looks like the limit will always be 1. So why isn't that differentiable at 0? Even though there's a discontinuity, there's obviously a discontinuity at 0, which from our previous statement would say, well, if it's not continuous, then it's not differentiable. But it sure looks like the limit is 1 pretty much everywhere. So let's take a look at this function and investigate the differentiability at 0. Okay, so I'm going to use the definition of the derivative at a point. I'm going to use the first definition that we talked about in the last section. And I'm going to look at the limit as x approaches 0 of f of x minus f of 0 over x minus 0. Now, because of the discontinuity, what I'm going to do, I'm going to break it into two parts. I'm going to look at the limit as x approaches 0 from the right of f of x minus f of 0. And I'm going to look at the limit as x approaches 0 from the left. Okay, and then we'll see what happens. Okay, now I could write a formula for this function f of x, right? I'd have to use a piecewise definition, but I could say, okay, when x is greater than or equal to 0, all right, the slope is 1 and the y-intercept is 1. So it looks like that would be x plus 1, right? Our formula would be x plus 1 for x greater than or equal to 0. Now, for x less than 0, then it looks like, again, it has a slope of 1, but the y-intercept is negative 1. So x minus 1 would be our formula. Okay, now, so then I can use the formula for f of x as we approach x from the left or the right, or as we approach 0 from the left or the right. All right, so let's do that. Let's look at f of x. So we're looking at the limit as x approaches 0 from the right. So those are values that are greater than 0. So I'm going to use the x plus 1 formula. Now the value of the function at 0 is the point that's filled in, right? And so that is going to be 1. Okay. And then x minus 0 is just x. So, okay, as you would expect, we can cancel plus 1 with the minus 1. We just get x over x. And so I'm just going to say that's 1, right? I can cancel the x's as well. I'm not going to write the limit again, though. But you can see that the limit is 1. Okay, that makes sense. All right. So now let's look at what happens as x approaches 0 from the left. Okay, now the formula is x minus 1 when x is less than 0. And so we're coming at 0 from the left, so that's less than 0. Now the value of the function, right, it's still that filled in value at 1. So we're going to get minus 1 all over x. All right. Now we have a problem that it doesn't cancel. We don't have it, the ones don't cancel. All right. So what do we have? We have the limit as x approaches 0. Oops, x approaches 0 from the left. And so we basically have x minus 2 over x, right? All right, now what happens to that as x approaches 0 from the left? Let's actually rewrite this again. The limit as x approaches 0 from the left. I'm going to divide both of the terms in the numerator by x. So I'm going to have 1 minus 2 over x. Okay, now 1 goes to 1 and 2 over x. What does that, we're approaching x from the left, so x is negative, and when we divide by smaller and smaller numbers, this is going to go to infinity. So it's going to go to negative infinity, but it's minus a negative infinity. So it looks like that's going to be infinity. All right, now you can see the problem, right? The limit from the right and the limit from the left don't match. So the limit as x approaches 0 of, I'll just write it f of x minus f of 0 over x, right, it does not exist. I'm just write d and e, right? That means f prime, right? This is f prime of x, or sorry, f prime of 0. That's f prime of 0. And so at 0, the derivative doesn't exist, and so this should have been a 0. All right, I was looking at 0, and it would be differentiable at 1, I think, but the f of x is not differentiable at x equals 0. So the answer here is no, it's not differentiable. All right, I'll meet you in the next video for one more little topic.